We'd like to thank Opera for supporting PBS, and you can learn more about them at the end of our episode. The James Webb Space Telescope has found galaxies that are too ancient looking for the young universe in which they were found. Now, you may have heard that, but JWST keeps finding them, and our recent efforts to solve this conundrum point in wildly different directions. Have we found galaxies older than the universe itself, or did we just learn something incredible about how galaxies form? Before we get started, a couple of quick announcements. First, we have some new data. Liking and commenting really does help get the episodes shared. So, please do both of those things. And we've also learned that the number one reason that people support us on Patreon isn't actually the perks. It's simply to support the Spacetime community and the work that we do. So, for those of you who do support, thank you so much. But don't get me wrong, there are perks, and they're good. There's a link in the description if you'd like to join. This really would be a huge help. Next up, today's episode is part of PBS Earth Month. PBS is celebrating by releasing a ton of great new episodes diving deep into our amazing planet. In particular, you might enjoy the latest episode of Be Smart, which explores the math, science, and history of the Mercator map, a flawed work of genius that, in more ways than one, changed the world. Links to that episode and the full Earth Month playlist also in the description. Next up, we're excited to announce our third celebration of a galaxy far, far away with our return of the geodesic merch. Because whether you're following a geodesic on a closed universe or reliving your favourite saga, you'll always know where you'll end up. And now until May the 4th, there's 10% off the whole merch store, with special deals if you combine your order with previous May the 4th merch. Now, onto the episode. Telescopes are time machines. Light takes time to reach us, so we see distant objects as they were when their light began its earthward journey. As our telescopes become more powerful, they see further, and so more and more of the past becomes accessible to us. The James Webb Space Telescope is one of the most powerful time machines ever built. It's powerful enough that it's discovered galaxies whose light has been travelling to us since the universe was just a little over 2% of its current age. The universe back then should look different, right? Those galaxies should look different. After all, this is when galaxies first started to grow, when they should have been vigorously forming many of their stars. They should look like hyperactive kids. Those types of galaxies probably are around back then, yet JWST has also seen much more developed adult galaxies, some of which look way too big and way too ancient looking for a universe that's only a few 100 million years old. Over the past year or two, this mystery has made the pop-sci rounds. That included some breathless speculation like the idea that the entire Big Bang model is wrong. If there are ancient galaxies 13 or so billion years ago, then how can the universe only be 13.5 billion years old? So far, we have not weighed in on this conundrum. Now, many others have done a fantastic job laying it out and debunking some of the foolishness. Dr. Becky in particular was on top of the progress as new data came in from JWST. So why should we cover it now? Well, first, a lot of you have asked for our take, and it's time to go on the record. Second, the evolution of this mystery has been quite an emotional rollercoaster, swinging from unsolvable to solved, and now there's new work that swings back in the direction of WTF. So let's talk about the current status of the early galaxy conundrum. And before that, let's talk a bit more about what we actually expect the early universe galaxies to look like. Galaxies pulled themselves together from tiny density fluctuations in the very early universe that we see as the dappling of the cosmic microwave background. The CMB reveals regions with tiny excesses of matter, hydrogen gas, but more importantly dark matter, which outweighs the gas by a factor of at least 5. As dark matter pulled itself together by gravity, it pulled the gas in with it. And as that gas compacted, the first stars were also born. These very early galaxies must have started small, but with pretty crazy star formation due to the enormous abundance of gas at that time. As those galaxies continued to grow, they collided and merged and eventually built themselves into the mature galaxies that we see today. We think we understand this stuff pretty well, or at least we thought we did. Between the precise CMB measurements and our theoretical understanding of gravity, star formation, etc., our computer simulations allow us to explore the possible growth scenarios for galaxies. We can predict, for example, that early galaxies should have been forming stars like crazy due to the enormous amount of raw material, the hydrogen gas, around back then. One thing that should be even more robust as a prediction is the size of dark matter halos. These are the giant pools of dark matter that encompass all galaxies and hold them together. Because dark matter should not be strongly affected by the complicated behavior of the gas in the stars, we have high confidence in our understanding of how those halos grew over time, or at least we thought we did. One very clear prediction of this whole model is that a lot of this halo growth should have happened in the first 10% of the universe's age. In that first 1.5 billion years since the Big Bang, there should have been essentially no very large halos, and so no very large galaxies. And that's what the theory and the simulation say. But to check these, we need powerful time machines, telescopes. Now, as our telescopes got bigger and our cameras got more sensitive, we were finally able to probe early enough times to properly test our models of halo growth. And this is where the problem started. Around 16 years ago, when our high redshift galaxy surveys, aka really far away galaxy surveys, finally reached these distances, we got some answers. And those surveys started seeing a few cases of what looked like giant halos at earlier and earlier times, and also the hint of overly red galaxies in the early universe. Galaxies that are actively forming new stars should be bright at short wavelengths because they have lots of giant, hot, short-lived stars. They are relatively blue in colour compared to older galaxies, and older galaxies that are no longer so actively forming stars should look redder because the short-lived blue stars have exploded already. Those earlier surveys didn't reveal anything crazy yet, just a handful of cases where galaxies looked too big and or too evolved compared to what was expected from our models. In 2018, Charles Steinhardt and team articulated this emerging tension in their paper, The Impossibly Early Galaxy Problem. But impossible things are impossible. It's right there in the name. So several not impossible explanations for these galaxies were devised. For one, we don't really see overly large dark matter halos directly. We only see the starlight, and then we use that starlight to infer the mass of the stars and then the mass of the halos that contain them. But that step requires assumptions, and if any of the assumptions are wrong, then perhaps we got the wrong halo mass. And the redness of the galaxies that suggests an old stellar population could be due to other things. And there are several other issues with these inferences besides, and I'll come back to possible solutions in a bit. But even if the galaxies that were found in these ground-based surveys were really too old-looking and too big-looking, well, we haven't quite broken all of astrophysics and cosmology yet. If we strain our models of galaxy formation, then we can potentially speed up galaxy evolution to show why these things exist by the time that the universe is 10% of its current age. What we'd really like to do is to look back even further in time to see if we can find the time when these galaxies were themselves growing. And that's what we did with the James Webb Space Telescope. JWST was designed to push this early galaxy game to new extreme limits. It's the largest telescope ever deployed in space, which means the most powerful. It's also designed to be sensitive to very long wavelengths of light, deep into the infrared part of the electromagnetic spectrum, the mid-infrared as we like to call it. That's important for these first galaxies because of the expansion of the universe. Their light has been travelling to us for much of the age of the universe. Because these EM waves are travelling through an expanding universe, they get stretched out, their wavelengths lengthened. This is cosmological redshift, and higher redshift means longer travel time and greater distance. For galaxies that we're interested in, this redshift converts visible and even ultraviolet light into mid-infrared, which is why JWST is needed. The first efforts with JWST used similar methods to our ground-based galaxy surveys. So maybe I give you a bit more detail on that. Now, the first thing that you do in a galaxy survey is to take some pics with different filters corresponding to different wavelength bands, and then you compare the amount of light in each filter. We call this photometric imaging. We can learn a lot of stuff from the ratios of filter brightnesses, the so-called colors. We discover candidate galaxies this way. We make a crude estimate of the distance because the color ratios suggest a redshift. We can constrain the stellar population, both the number of stars and the distribution of different types of stars. For example, the redder colors mean an older population with few massive stars. So what did JWST find? Well, first it confirmed the presence of overly massive and overly old-looking galaxies from the earlier studies. And remember, that was from a cosmic age of around 10%, which is a redshift of around 4. Now, a critical advantage of JWST is that it's sensitive enough to do proper spectroscopy on these galaxies. It can measure their spectrum, the amount of light as a function of wavelength. These spectra confirmed that the redshift are indeed very high. They also confirmed that the redness of the spectra is due to highly evolved stellar populations rather than, say, there being a lot of dust in these galaxies, which can cause a similar reddening in photometric analyses. With these confirmations of old-looking early galaxies, researchers more broadly really started to pay attention. The media started to pick up on this when JWST pushed to greater distances and earlier times and kept finding these things. Currently, the earliest candidate giant evolved galaxy discovered by JWST is at redshift of 7.3 at just 5% of the universe's age. Now it seems we have a real conflict with our models of galaxy formation. Dark matter halos too large and stellar populations too evolved for the short amount of time that they've had to develop. And this is why we started to hear some hysterical claims that the universe is twice as old as we thought, or that the Big Bang model is completely overturned. It's not, and it isn't. There's just so much independent corroboration of our model of an expanding 13-point-something billion-year-old universe. You can't point to one admittedly intriguing discrepancy and decide to throw the baby universe out with the bathwater. There are much more parsimonious explanations for our improbably early galaxies. Let's look at one of the most compelling. Remember that when we calculated the masses of these supposedly gigantic dark matter halos, we based them on the starlight that we see, and that requires an understanding of the relationship between these two things, the starlight and the dark matter halo mass, and that involves assumptions. Here's how that works. One assumption is that the halo mass is connected to the mass in stars, and that stellar mass is connected to the amount of light that we see in those stars. But we don't see the light from all of those stars. Typically, the light we collect is dominated by the brightest stars in the galaxy. We then have to decide on the relative numbers of different types of stars so we can extrapolate from the observed starlight to the mass of the stars, seen and unseen. And there's another assumption. And yes, from then we can get to the halo mass. Knowing the distribution of stellar masses in a galaxy on the other side of the universe takes some guesswork, to say the least. And maybe the biggest unknown is something that we call the initial mass function, the IMF. It tells us the relative number of stars at different masses that form when a burst of star formation happens. We typically use the IMF that's been measured for the Milky Way galaxy, sometimes with various refinements. But we don't know that stars formed with similar mass distributions in the early universe, and they probably didn't. For example, when there's less heavy elements around from generations of old stars, it's easier to make really gigantic stars because gas clouds don't fragment as much when they collapse. That could give those early galaxies what we call a top-heavy IMF. So more massive stars form in a given burst of star formation relative to what happens in the Milky Way. And more bright massive stars mean that these galaxies would be overly bright for a given halo mass. So if we're determining halo mass from the light of these massive stars, then we overestimate halo mass. Such a top-heavy IMF is probably the leading contender for explaining the apparent giantness of the dark matter halos, and this may even solve the conundrum. But the mystery does not stop here. A new study has found exactly the opposite result to this. This study claims to have identified a sample of galaxies that are what those impossibly early galaxies became in this part of the universe. And because this sample is much closer to us, we can detect the light of much fainter stars, and we can figure out the initial mass function down to much lower masses. And the result is bad. This study found that the IMF is actually bottom-heavy in those galaxies. There are way more low-mass stars, little red dwarfs and whatnot, compared to the Milky Way, for example. And definitely very bottom-heavy compared to what we think a top-heavy IMF might look like, the top-heavy IMF that was supposed to solve the problem of the impossible galaxies. And in fact, this bottom-heavy IMF worsens the problem. An excess of low-mass stars means that when we convert galaxy light to stellar mass, we underestimate that stellar mass and presumably underestimate its related dark matter halo mass. And that makes it even harder to figure out how those things grew so fast, so quick. Okay, so before we join our crazy uncle on the anti-Big Bang conspiracy Facebook group, some words of caution. We don't really know whether this new study really did successfully identify the modern counterparts of our impossible galaxies, and the authors admit that, calling them likely descendants. We also don't know what complicating interactions these galaxies could have had in the intervening 13 billion years to muddle the IMF. And we also don't know that a bottom-heavy IMF rules out an IMF that's also top-heavy. In other words, there could be an overabundance of low-mass stars and of high-mass stars, all compared to masses around that of the Sun. And it is plausible to assume an IMF like this that would still bring down those early halo masses. There are similar challenges in explaining the apparent redness of the early galaxies. The key here is that we need a way to shut down star formation much more quickly than we thought likely. Perhaps the leading contender is quite awesome. Early quasars, supermassive black holes in the hearts of these galaxies, blasting out radiation and winds that heats up and expels gas, so stars stop forming and the population can evolve quickly. We know that this sort of feedback from quasars happens, but now we need to understand why it's so extreme in the early universe. That involves very rapid growth of supermassive black holes, yet another very real and very interesting problem. The most likely solution to all of this is that we're going to learn an enormous amount about the surprising processes behind structure growth, star formation, black hole seeding and growth, and who knows what else. And once we figure it out, the impossible early galaxies will become more than just possible, they'll become inevitable, a natural part of our updated understanding of our early spacetime. Thank you to Opera for supporting PBS. Opera offers a useful way to explore complex topics and the world around us. If your research requires a lot of tabs, then Opera's tab islands and tab traces can help keep your tabs organized and visible. With tab islands, you can group your tabs based on theme, project or context, or whatever organization makes sense to you. Just hover over the island and you can name them, coordinate them by color, and expand and collapse as needed. And if you're the type to keep 30 or more tabs open while going down a research rabbit hole, Tab Traces lets you track your most recently used tabs with a subtle visual underscore. The darker the underscore, the more recently you visited that deep dive. Opera's split screen feature is designed to help users make use of screen space by letting you choose from vertical, horizontal, or grid layouts. When you drag your tabs downward, Opera splits the screen up to 4 resizable ways. If you'd like to try out all the features of the Opera browser, there's a link in the description.